Perfect. So if you look at the very first slide, alkene is of two types, internal alkyne and terminal alkyne. Terminal alkyne means triple bond at the terminal position, and if you balance this, you know that this carbon have a hydrogen, and this is CH3, this is C and CH3. So first slide is a category of alkyne. So we can divide the alkyne into terminal and internal alkyne. Now the very first reaction is catalytic hydrogenation of internal alkyne. So catalytic hydrogenation means it is a reduction in presence of H2 with PD in presence of charcoal. So the key point is under these conditions, the cis alkene is difficult to isolate. In presence of poison catalyst, it is possible to convert alkyne into cis alkene. So simply we can say this is CH3, C, triple bond C and CH3. And if you are going to take H2PD, it would convert triple bond into single bond. So this is CH3 and this is CH3, this is CH2, this is CH2. So this is the reduction of triple bond into single bond. Now next is Lindlar catalyst. This is very important. This is CH3, C. Which one you talking about? This. It would give you cis alkene. Listen me. No, not the, first of all, previous one is not a trans alkene. This is, the last one was alkane, single bond. Clear? So alkyne reduction is 3 basically. Alkyne reduction is 3. 1, it can give trans alkene. Second, it can give cis alkene. And last, it can give alkane. So trans alkene would be in presence of sodium and lithium in liquid ammonia. Sodium in liquid ammonia. Cis alkene, H2 with Lindlar. H2 with Lindlar. And only alkane, H2PD. Make sense? So this is a Lindlar H2. That's why this internal alkyne would be cis alkene. So this is cis alkene. Now next trans alkene, you can see sodium or lithium in liquid ammonia, and this is my internal alkyne and it becomes trans alkene. Trans alkene. Make sense? Please tell me. Perfect. Suppose we have this question. Okay, we have this. Now you can see the best way. This is my internal alkyne. We are using H2 with Lindlar. So you know that it can give you cis alkene. So we have cis alkene. Now next is sodium or lithium in liquid ammonia. That gives you trans alkene. And now you can convert alkene also into alkane if you are going to react with H2PD or PT. Okay. Both can convert alkene into alkane. And if you are going to convert alkyne directly into alkane, then we can use H2PT. Make sense? Perfect. I would like to give you a question. Suppose we have this one and it is treated with H2PD or PT. A. Second, treated with H2 with Lindlar. This is B. And third, treated with sodium and liquid ammonia, which is C. Could you please, if do you have my contact number or my messenger, any of my ID? Do you have? Okay, no worry. Let me draw this. Let me draw this. So if you look at the very first one, suppose H2PD, you know that this alkyne would be alkane. So we can put a single bond here, and you know that this is a ring, and here we have CS3, and this is single bond, so we can put two hydrogen here, two hydrogen here. Make sense about it? Now next, sodium and lithium in liquid ammonia, which means trans. So how could you generate trans one? So first convert triple bond into double bond. Now both the chain would be opposite end. Suppose this is CS3, then it would be a ring here. And here H, here H. So this is trans. Now next is cis. So same thing, carbon double bond carbon, but this time we are going to put methyl and the ring in the same side. And H and H. Make sense? Perfect. Next is hydrohalogenation with HBr, and it is very easy. It's just like same as alkene reaction. Alkene treated with HBr. You know that alkene treated with HBr means you can apply Markovnikov's rule. Markovnikov's means negative part of the reagent would attack on the carbon that is more substituted or less hydrogen. So this one have a hydrogen, but this carbon have no hydrogen. So Br is going to attack over here. So it should be here. Next mole, again HBr, again same thing, negative part would attack on the carbon which is less hydrogen containing or more substituted, means more carbon. So Br again going to attack this carbon. So you can see carbon had both bromine. Clear? For example, suppose you have this one. And we are going to react with two equivalent of HBr. So both the bromine would attack on this carbon because this one has less hydrogen. So bromine, bromine, CH2, CH3. Make sense? Next, hydrohalogenation with HBr, but this is internal alkyne. So this internal alkyne, now this carbon and this carbon, they have equal number of, hydrogen, means they don't have hydrogen. So this negative has both the opportunity. It can attack either this carbon and it can attack on this carbon. So both possible products. And in the next mole of HBr, Br is going to again attack over this carbon and again over here. So you have two different product. Make sense? Why does it happen? Because this internal carbon are different from each other. You can see this neighbor is CH2, CH3, but this carbon neighbor is only CH3. So both the carbon are different in nature. That's why we have two different alkenes. Similarly, we can do radical addition of HBr. You know that it is peroxide. HBr with peroxide, it means anti-Markovnikov's. Anti-Markovnikov's means Br attack on that carbon which is more hydrogen. So this carbon has more hydrogen, so Br would attack over here. So this is my double bond now. And here we have a bromine. So this double bond is showing cis trans or E and G. So if one product is supposed to be G, then another one would be E. So you have a mixture of E and G. Clear? Make sense? Perfect. Interconversion of dihalide. So this is a terminal alkyne. And if you are going to react with HX, HX supposed to be HBr, HCl or HI, you know that this is internal carbon and this is terminal carbon. So you can apply Markovnikov's rule And you know that according to Markovnikov's, negative charge would attack on the carbon which has more carbon, means less hydrogen and more carbon. So this carbon would be, so over here, and it is excess amount, which means 2 equivalent. So another time X is going to attack on the same carbon. And if you are going to convert this to this, then use this base in presence of ammonia, because this is elimination reaction. Elimination means this is alpha halogen, this is beta hydrogen. So first elimination is a loss of X and this hydrogen, so there is a double bond, X and double bond CH2. Now another mole of elimination here, because again we have NaNH2 liquid ammonia, NH3H2O. So again this is alpha, this is beta. So again loss of this X and this hydrogen. So we have a triple bond. Make sense? So simply we can say gem dihalide to alkyne is an elimination. This is elimination. And alkyne to gem dihalide is an addition. Predict the major product of expected or each of the following reaction. Easy. HCl, so Markovnikov, Cl would attack over this carbon and excess means 2. So it should be like this. Cl, Cl. Make sense about A? Please tell me. Perfect. Now second B, it is elimination. You know that, and it is excess. Excess means both the bromine is going to eliminate with respect to this beta carbon. So we have a triple bond overall here. Make sense? Perfect. Now look at this one, excess NaNH2 with H2O. So it would give you a triple bond. Now next HBr with H2O2. So you know that this is anti-Markovnikov. So Br would attack over this carbon. And double bond. So this is supposed to be E, then another one would be Z. Like this. Make sense? Now same here, NaNH2 base H2O. So elimination. And then excess HBr. Excess HBr means both the Br should be this internal carbon. Like this. Make sense? Perfect. So you have the answers, you can match. Next is halogenation with Br2. You know, most of the reactions of alkyne is same as alkene. If you remember, we have alkene supposed to be, and we are going to react with Br2. So both the Br should be in anti-direction. One should be here, one should be down, like this. So same here, one equivalent would give one addition of bromine over internal carbon and one on the external with anti-direction. And another mole of Br2, same, one over here and one over here. So overall 4 bromine. Make sense? Suppose you have this one. And we are going to react with Br2, suppose 2 equivalent. Then 2 bromine should be here and 2 here. Clear? Perfect. And one more thing I would like to tell you here. Okay, that's it. Yeah, that's important. Next is hydration of internal alkyne. Whenever the reaction is hydration, it means addition of water. Addition of water. So whenever you have unsymmetrical alkyne, whenever hydration of unsymmetrical means if you are going to break this, you can see the left and right is different. So this is called unsymmetrical. Internal alkyne yield a mixture of ketone. So you have two different ketone, one over this carbon and one over this carbon. So I am just going to tell you direct product writing. Suppose we are going to draw the product of this internal alkyne with this. So first you can keep ketone over, suppose 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. So you can make a zigzag 1, 2, 3, 4 and 5. So you can keep ketone at number 2. Another product 1, 2, 3, 4, 5, and then you have to keep ketone at number 3. So this is a mixture of product. Makes sense? It makes sense. Perfect. So addition of one equivalent of water followed by, so basically this is a direct product writing, means this is ketone as a final product, ketone as final product. But the intermediate product is here enol, means first it would form enol, then enol tautomer to give you ketone. Clear? Makes sense? Yes, of course. Let me tell you the enol part. Okay, listen me, if you are going to write down the product of this reaction, so first thing is that addition of H2O, it means H plus and OH ion. This is simple method. So you have to apply Marconi-Cops. Marconi-Cops is what? OH attack on the carbon which is supposed to be less hydrogen or more carbon chain. So both the carbon having same nature. So you have opportunity to add OH either this carbon or this carbon. Suppose I am going to attach OH at number 2. Then CH3 COH double bond CH CH2 CH3. It makes sense this kind of enol. Please tell me. Now second opportunity, if you are going to keep OH over number 3 carbon, means enol at number 3. So CH3, CH, double bond, C, OH, CH2, CH3. Clear? So we have two different enol and enol. Suppose enol 1 and enol 2. Make sense? Do you know how to convert enol to keto form? Do you know? Please. Yes, tautomerize. Yes, tautomerize. Do you know how to convert? Okay, let me tell you the trick. Suppose we have this, first I am going to discuss keto to enol conversion. Suppose this is my keto form and we want to draw its enol form. So this is the alpha carbon. The carbonyl neighboring carbon is called alpha carbon. So one of the hydrogen of alpha, attached to oxygen and double bond back to this alpha carbon. So you have CH2 double bond C, OH and H. Suppose you have this ketone and you want to draw its enol. So this is alpha H. So simple method is hydrogen back to oxygen and double bond back to alpha carbon. So this is OH and here double bond. Make sense? This enol. Now reverse process means enol to keto. It's easy. Look at here. Enol to keto means hydrogen back to alpha carbon, double bond back to the oxygen. You can see. Hydrogen back to alpha carbon, double bond back to the oxygen. You can see. Same here. Suppose we have this enol and we want to draw its keto form. So hydrogen back to alpha carbon, double bond, this oxygen. So CH3, C double bond O, CH2, CH2, CH3. Same here. Double bond here and hydrogen over this carbon. So CH3, CH2, C double bond O, CH2, CH3. Make sense? Next is hydration of terminal alkyne. So terminal alkyne is very easy because we have clear Marconi-Cops. So this is carbon having one H. This is without hydrogen. So OH is going to attack over this carbon. So it would be CH2 double bond C, OH, CH2, CH3, and now you can do tautomerism. So double bond should be here and hydrogen back to this carbon. So CH3, C double bond O, CH2, CH3. You can see. Make sense? So it's a clear Marconi corpse basically. Internal carbon have, both the carbon are same, so we have two different products. So this is tautomerism. I have discussed this here. So you can see this is my hydrogen at alpha and double bond here. So we have keto. And if you want to convert keto to enol, then you know that hydrogen back to this carbon, double bond should be here. So acid catalyzed as well as base catalyzed. Tautomer is given by only those aldehyde and ketone which has alpha hydrogen. For example, this carbonyl neighboring carbon is called alpha carbon and this carbon have H, so it can give tautomerism. But if you look at this carbon, this is carbonyl, neighboring is alpha, but here we don't have a hydrogen, so no tautomerism. Or even this one. Carbonyl neighboring carbon is alpha and here we don't have a hydrogen, so no tautomerism. Make sense? So alpha hydrogen is a necessary condition. You can see carbonyl neighboring carbon is alpha. Alpha have 3 hydrogens, so it can give tautomerism. And carbonyl neighboring carbon is alpha. We don't have a hydrogen, so no tautomerism. This is the acid catalyzed tautomerism, the mechanism part. So it's conversion of enol to keto form. So acid catalyzed means H plus in presence of H2O. Or we can say as H3O plus. Clear? So this is OH group. So OH is going to, this double bond is going to, grab this hydrogen. So you have basically it donates its electron and then double bond attack over here. So simply you have this O plus H double bond and this carbon have H, H, H like that. Make sense? And the next step, you have H2O. H2O deprotonate this H. So simply you have ketone. Clear? So this is enol to keto form. Now the next is base catalyzed. So base catalyzed, you know that this OH is, this hydrogen is very acidic. This hydrogen is very acidic. So base is going to grab this H. So you have O negative, which is acting as an enolate. Enolate means oxygen is negatively charged. And now you can draw its resonating structure. It would donate this double bond break. So now this negative and this negative grabs the hydrogen from H2O. So it is a simple hydrogen and this is aldehyde. For example, suppose we have this enol. This is my enol. Let's talk about the mechanism. Here we have a base. So base would grab this H. So this is negative. Now you can draw in this way. This is H2O you have. Because base grabs H, so it becomes H2O. Now look at this protonation step. O minus revert the electron. This double bond grabs this H. So simply you can see we have a ketone and this one have H like this. So this is my keto form. Make sense? Hydration of terminal alkyne. This is very, very important. This is called hydroboration oxidation in salt. HBO. And how can you memorize anti-Markovnikov? Because we have H2O2. So H2O2 means anti-Markovnikovs. And anti-Markovnikovs means the OH is going to attack on the carbon which has more hydrogen. So look at this carbon, it has a hydrogen, and this carbon we don't have hydrogen. So the best way is trick, keep carbonyl group on the triple bond carbon which has a maximum number of hydrogen. So this carbon have a hydrogen. So you have to keep a double bond over here. Means HC double bond O, then single bond. This becomes CH2. This carbon is CH2 and this is CH3. Make sense? Suppose you have this terminal one and we are using the same reaction HBO, hydroboration oxidation. So what would happen? The aldehyde would be at this carbon, double bond OH. Make sense? So now this is alkyne and you are going to treat with H2SO4 with Hg. This is simple hydration reaction. So hydration means the OH would be over here. Marconi-Cops you can apply. So OH attack over this carbon. So you can keep carbonyl at the internal carbon. But this is hydroboration oxidation. So you can keep carbonyl at the outer carbon, terminal carbon, the carbonyl group. You can see the terminal carbon. Make sense? So if you have a terminal alkyne, this is terminal, and you want to draw ketone, then you can do hydration. If you want to draw aldehyde, then you can do hydroboration. So this is a alkyne, this is terminal alkyne as you can see, and the key to carbonyl group at internal carbon. You can see this carbon, carbonyl group. And you know that internal carbon can be carbonyl hydration. Very good. Very good. If you have carbonyl at suppose this carbon, then you can go with hydroboration oxidation. Okay. So in Orgo 1, it is important because sometimes you have a reactant and product and then you have to figure out reagent. In DAT also it is very important. Nowadays it can be asked in this type of question. Suppose this is and any of the option is A, then B you can use hydroboration oxidation, C you can use multiple synthesis. So it can be asked. Next is SN2 addition with acetylide. So NaNH2 is a base. Is H2SO4 always used for hydration? H2SO4 with HgSO4 you should say. So overall it's a hydration, okay? Means addition of water. Now this is base. Base would grab this hydrogen. So it would grab this hydrogen. So now this is negatively charged which can act as a nucleophile. So this is my primary halide and you know that whenever nucleophile have a primary halide, this reaction would be considered as SN2. So you can see this carbon, suppose carbon number 1. So the rest of the part of the triple bond would remain same, CH3C, triple bond C. This is carbon 1. Now carbon 1 bonded to the bromine containing carbon, so carbon, and this carbon bonded with CH2, CH3, CH2, then CH3, and here 2H as well. So whenever you have such a kind of question, always try to mark the numbering so it can give you a clear idea about the carbon of the chain. Clear? Next, SN2 reaction with slide in ketone reaction. So whenever you have a nucleophile and you have a carbonyl group, so the reaction would be nucleophilic addition. Okay. So it would grab this H. So negative here nucleophile attack over this carbon, it breaks. So now look at the connectivity. This is O minus. And suppose this is my another carbon chain, these two, these two. And now this is the carbon of the triple bond, And now we have a triple bond and then CH3. In the next step, we have H2O, so O minus protonates. So it would be OH. Clear this reaction? So this is example of nucleophilic addition. Next again same, base would grab this H, again nucleophile. And this is epoxide, this is basic medium. So whenever you have such a kind of thing, then it would be SN2 in the second step. SN2 means it would attack on the carbon which is less substituted. So you can mark as 1 and 2. So it would attack at number 1 carbon and it breaks. So suppose this is carbon 1, this is carbon 2. So number carbon 2 have O minus, and after protonation it would be OH. And then side chain is methyl. And now number 1 carbon have a triple bond, and then triple bond with another methyl. Make sense? Please tell me. Makes sense? Okay. Next is ozonolysis, oxidative cleavage of internal alkyne. So this is very, very important and very easy as well. So look at this breaking. Terminal carbon becomes CO2 while internal carbon would be carboxylic. So here both are by internal carbon, both. So you can break and keep carboxylic this one and keep carboxylic this one. So you have 2 mole of carboxylic. Make sense? Please tell me. If suppose this is supposed to be in suppose terminal alkyne like this. So same reagent I am using. In this case, this is my internal, so it would be a carboxylic. And this is external carbon, so it would be CO2. So product would be this. Clear? And here we can use either H2O2 with O3 or KMNO4 with heat. Next, ozonolysis, oxidative cleavage of terminal alkyne. Same, we have done this already. So you can break, it would be CO2 and it would be carboxylic. So you can see. Alkyne formation from double elimination of a vicinal dihalide. Same thing we have done. NaNH2 is a base. Suppose this is my alpha, this is beta. So beta have a hydrogen. So loss of bromine and this hydrogen. So we have a double bond over here. And again NaNH2, again same process. This is alpha, this is beta, we have a beta H. So now you can eliminate this bromine and this hydrogen. So overall we have a triple bond. Clear? Identify the reagent that you would use to achieve each of the following transformation. So this is my alkyne, and you can see this is looks like trans type. So you can use here what? Lithium, sodium, liquid ammonia, and it is cis type. So you can use H2 with Lindlar. Clear? Same here, alkyne, and this looks like trans type. So you can use here H2 with Lindlar. And this is simple alkane, so you can use H2PD. Make sense? Predict the major product of the following reaction: easy, NaNH2, sodium, liquid ammonia. So this alpha, this is my beta position, but we don't have a hydrogen at this beta. This is elimination, yes. But this beta, we don't have hydrogen. We have hydrogen over this beta. Clear? So you can keep a double bond first by loss of this Br and any one of the hydrogen. So it would be this double bond CH2. Clear? This time we don't have excess base. So it's just one elimination. Here we have excess. So you can do multiple elimination. Means this is H, this is H, Here we have one H. So one chlorine, suppose this chlorine and this hydrogen, so we have a double bond. And now this chlorine, this hydrogen, so we have a triple bond. Clear? Makes sense? Perfect. Draw the major product expected to each of the following alkyne treated with aqueous acid in presence of mercuric. Means it is talking about H2O, H2SO4 with HgSO4. Yes, this is hydration one. So you can add carbon, here OH, okay? Here OH. Finally, you can keep a ketonic group over here, means carbon, single bond carbon, double bond O, like this. Make sense? Clear? And in this case, we have a multiple product because they both are same one. So first you can keep this carbon as a carbonyl in one of the product, and second, suppose this is 1, this is 2. In second, you can draw ketonic group over this carbon. Make sense? Same 9BBN H2O2 also hydroboration oxidation. This bottom one is also hydroboration oxidation. This is O3 with H2O, same as the oxidative ozonolysis. This is the answer of those questions. You can match. Okay, makes sense? So this is all about the alkyne. In the next session, I will share this slide. So you can, could you please turn on your camera? Let me stop the recording first.